Lesson 32 is going to take us through the mathematical application of what we've learned about circular motion so far. And it starts off with this nice pretty picture of the orbital speeds of the planets. Kind of an interesting diagram. As you can see, here's our Earth right here. Oops. And here's the Earth. We are presently moving at about 30 kilometers per second through space. And as you get closer to the sun, because of the gravitational force being so much stronger, the planets get faster. Once you get to the outside, you got poor little Neptune only going at 5.43 kilometers per second. It takes Earth 365 days or 1 year to get around the sun. This velocity here, and given this distance away from the sun, it takes Neptune 165 years to get around the sun once. So if you are a Neptunian and you are 2 years old, on Neptune, you are actually 330 Earth years old. Of course, there's probably no life as we know it on Neptune because of its extreme cold and inhospitable environment. Okay, here we go. Let's get through this. So most of this we've gone through already. We'll go through it fairly quickly. Here's the formula for measuring circular velocity, and it's all based on good old faithful, good old V equals D over T. But this time, as we're moving in a circular path, we're going to use the circumference of the circle for the distance. And that's why D gets replaced with 2 pi r, yielding this formula, which we then change a little more. And since we're dealing with something going in a circular motion that goes around in the circle, in a periodic motion, in other words, it goes around the circle, takes the same amount of time to go around the circle each time, its period, we replace little t with capital T, and here it is. It's on your formula sheet. That's the formula for the velocity of circular motion. An example here, determine the length of a student's arm if she can swing a pail around 5 times in a circle in at 2.72 meters per second in 7.5 seconds. So we've just got somebody spinning something in a circle, and we're determining this is the length of the student's arm. That's what we want to determine. Here's our formula. We're solving for R. R equals cross multiply VT over 2 pi, cross multiply and divide. The velocity we have. Oopsie. The period, we're going to have to calculate that, because if it says you can spin it around 5 times in 7.5 seconds, therefore we want to know how long does it take to go around once. And you can probably see the answer is pretty straightforward. It's just 7.5 divided by 5. But if you want to do that algebraically, again, using a proportion, you could say, well, if it does 5 cycles in 7.5 seconds, how long does it take to do, oopsie, not a mistake, mistake number 2. How long X does it take to do 1 cycle? 1 cycle, and then cross multiply and divide, and you get X equals 1.5 seconds. So that's the period. That's how long it takes to do 1 cycle. We can now plug that into our formula. Two pi is a constant. Stick everything in, and you get 0.65 meters, which then you ask yourself, is that a reasonable answer for the length of a student's arm? Yes, it is. If you got 17 meters, then that's a pretty long arm. Or if you got 0.01 meters, that's a pretty short arm. So 0.65, just over half a meter, that's a pretty reasonable answer for the length of a student's arm. Onward, centripetal acceleration. Here's the formula for centripetal acceleration. It's on your formula sheet. Centripetal acceleration equals the velocity squared divided by the radius. Let's go right on to a question. What is the centripetal acceleration of a person driving at 60 kilometers per hour in a traffic circle that is 120 meters across? So 120 meters across. If it's 120 meters across, then that's its diameter, and therefore the radius equals 60 meters. Centripetal acceleration equals the velocity squared divided by the radius. The velocity given to us in kilometers per hour, we need to convert to meters per second. Don't forget to square it. Stick all that into your calculator, and that is going to give you an answer of 4.6 meters per second squared. So that's the centripetal acceleration of the person driving in the car. Now, just while we're here on example number 2, we're just going to, when we go to example number 3, we need to derive a formula for it. Now, this formula is given to you on your formula sheet, but it's way more important in physics or in any science that you learn how to derive formulas, not just memorize formulas. That really doesn't help you. If you want to make your brain bigger and better, then learn how to derive formulas. So let's derive a couple of formulas. Hope you left enough space. I should have told you to leave some space when you're writing your notes here. So here's a formula we've learned on your formula sheet. And here's a formula we've learned. And this is a pretty easy derivation. You can see what's common to both formulas. Well, the radius is common to both formulas, and the velocity is common to both formulas. So let's just go with the velocity. I mean, you can do the radius if you want to get another formula. But if we take this velocity here, velocity equals this value, 2 pi r over t, and substitute it in here, we're going to get a new formula for the centripetal acceleration, and we'll discuss why we do this in a minute. AC equals OT all squared over R. So we've just substituted this entire value into the, we square it, and then we simplify that. I'm just going to do it over here. So boost it to the mic, and we get 4 pi squared R. Well, let's do the whole thing, just so you can see how it works. It's going to be R squared over T squared all over R, which is then going to be 4 pi squared R squared over T squared times the reciprocal, right? Remember when you're dividing, if you got fractions and you're dividing, you multiply by the reciprocal. And that serves the purpose of canceling that R with that R, and you end up with this. So there's a new derived formula for the centripetal acceleration, and the importance of that formula is now you don't need velocity. As we go through physics, you'll discover that velocity is sometimes hard to measure. However, radius is easy to measure, and period is easier to measure than velocity. So that's why this formula here, this derivation of the formula, is fairly important. It allows us to calculate centripetal acceleration without knowing the velocity. Okay, on to example number 3, and then we'll do this video in 2 parts. So example number 3 says, what's the acceleration of a horse running around a circular track with a radius? So this time maybe visit the radius once every 12 seconds. So if it goes around once every 12 seconds, then that 12 seconds is the period. And we're trying to find out the centripetal acceleration. And there is where this formula comes in very useful. Just plug in the numbers. It's a pretty straightforward one. We'll just give you the answer, and the answer turns out to be, what does it turn out to be? Turns out to be 10 meters per second squared. Okay, now if you, I mean, you could have easily done this problem without this formula here. It just would take 2 steps. So let's say I wanted to do it using another method. In step 1, I could find the velocity using this formula. And in step 2, I could find the centripetal acceleration using this formula. So there's just 2 different approaches to this problem, one using the derived formula and one using the formulas that we had already learned. Either way will give you the same answer.